So, from the last class where I discussed friction in many situations, on an inclined plane, etc., etc., today I'll talk about rolling friction, which is a very important aspect of friction. For example, if we take a ring or a sphere, the ring may be annular and it may be solid, okay, and it rolls over on a surface without slipping over a horizontal plane. In principle, this kind of a motion of rolling will suffer no friction. The question is why? I have made a very bold statement, but the question is why? It is because at each and every instant of time, if I have this ring or a ball rolling, you can see that there is a single point at each instant of time, and that single point, one point is in contact with the plane, and the plane and the contact point has no relative motion. The contact point has no relative motion because it's just a point, and there is hardly any area in contact with the surface under consideration. In practice, however, some rolling friction exists, and in order to keep the body rolling with the same speed on the plane that we are talking about, some kind of a force is required to keep the body rolling. Some small force is required to keep the body rolling, and this rolling friction, the content of it, the extent of it, and the value of it is very small as compared to the static or sliding friction that we have, and it is 2 to 3 orders of magnitude smaller than the static or sliding friction which exists. However, as I said, that during the rolling there are surfaces in contact, because the two surfaces that we are encountering here, the horizontal surface over here and the ball or the circular ring, etc., whatever is rolling here, both the bodies, during the surfaces in contact, they get momentarily deformed because of their weight factor, because of their reaction. So reaction forces, they make it momentarily deformed, and therefore some finite area is in contact, that of the ring or the sphere, and also that of this thing. So there is a momentary deformation, and it's not a point, but some finite area is in contact. Now, opposing force is provided by the component of the contact force, which is parallel to the surface, okay, which is parallel to this surface under consideration, okay. Now, the wheel was invented. The rings and spheres and all that kind of bodies in motion with regard to that. So what it did, when the friction is undesirable, when the friction is not desirable, friction is undesirable. Why? Because if there is friction, then there is a lot of dissipation of heat and lot of things are done which are not required, okay, then what we do many things. Like we can use lubricants, or we can use lubricants, or we can put in some kind of this thing, okay, I'll just take it off, and some kind of a pins that we can make there. Suppose this is one surface of a machine. A machine is having one ball kind of a thing, another ball kind of a thing, part of the machine, and in between we can put in some metallic things with the lubricants inside, so that the total amount of heat which is generated between the machine parts is small. Also, what can be done is that you can have, for example, this effect can also be obtained with the help of a cushion of air, and the purpose of these ball bearings is done by the surface, for example in the case of a hovercraft, where a craft is made to worker. In some of the Japanese trains also they have elevated rails. The wheels are elevated where the road, and there is a cushion of air so that the friction is minimized. But sometimes the friction is desirable. For example, if you want to apply brakes in automobiles or other moving things, then we must stop the car, stop the truck, etc. with the help of applying this thing. So next we go, after this brief introduction, and you can go through the book. Any book will explain to you many more things, examples, etc., which I am not going to take here. I will go for the friction which is obtained on a circular path when, for example, you have a flat road or you have an inclined road. The effects of the two, the flat road and the inclined road, when you go in a circular path. In a circular path, remember that we learned that we need to have a centripetal acceleration which has to be provided by something. For example, in the example that we took on horizontal plane, there was a string, there was a mass, there was a center, there was a pivot, and my mass was going round in a which is just similar to our Earth going around or other planets of the Sun going around the Sun. Of course, their orbits are elliptical. We will have occasion to discuss them, but the ellipticity is so small that the path can be taken as a plane path, and on that the motion is sort of circular, and then there has to be centripetal force, centripetal acceleration, etc., which we deal shortly. So, to study the rolling friction further, I'll discuss a very simple case of a circular motion where we are conducting a circular motion with the help of some kind of a vehicle on a level road, and basically this should be a level field, okay, a plaza kind of a thing, where whatever radius you want to take for this vehicle you can take. we can see that the car here is moving in this situation, anti-clockwise direction here, and with constant speed v. But the thing is that the speed is constant, but the direction of the velocity vector is changing. And for changing the velocity vector, there is required a force, some kind of an effort, which should be perpendicular to the direction of the motion of the car, of the vehicle. The motion has got a radius of capital R from the center to this point on the path that the vehicle is taking. And we know, and we have discussed it before, in the case of a horizontal motion in a circular path, that associated with this motion is a centripetal acceleration, A is equal to v square upon r. And this centripetal acceleration actually is provided by the frictional forces which are responsible for the circular motion. Now what will happen? Let us try to find out the maximum speed that we can move this vehicle on this level road, on this plaza, for a radius of curvature equal to r. So it's very simple. We just define the centripetal force, Fc is equal to mv square upon r. Okay, the acceleration becomes equal to this force divided by the mass of the vehicle. So it becomes equal to v square upon r, which we can also tell as, I'm just writing it for you to recall, that in that circular motion, motion in circle, we have an angular velocity which is omega radians per second, and the velocity is equal to r into omega. Also, when I draw a free body diagram, so I told you the free body diagram is obtained by concentrating on what are the forces which are acting on the body, and not by the forces the body exerts on other bodies. So if there are no deformations, etc., and this is the road that we have, this is the path that the body is taking, this side there is the center of the path and the body is moving, then the normal reaction is N, which is the manifest of, I told you, electromagnetic forces, and the gravitational pull of the earth, which is equal to mg. So because there is no acceleration in the vertical direction, in the vertical direction the acceleration is equal to 0, so the net force on the system should be equal to 0, or I can write N minus mg is equal to 0, so N is equal to mg. Now Fc, centripetal force, is provided by the component of the contact force between the road and the tires of the vehicle. So there is another point that should be borne in mind, that it is the static friction which works in this case, because the dynamic friction is less than the static friction, so we take the limiting friction, static friction case, and we have the mu s. Okay, so it will say that for the motion to take place, Fs must be smaller than or equal to mu s into n. Okay, by definition, because Fs is proportional to n and is equal to Fs is equal to mu s into n, and this is equal to mv square upon r. So we can write that our v square, this I multiply by r here and divide by m here, and I get mu s n r upon m. And of course, for n I am going to write as mg, so m and m are going to cancel out, and I will get a relation mu s into rg. So V maximum, under the condition that it is equal to, Fs is equal to mu s into n, we get the maximum velocity which we can achieve for the target radius to be achieved. This is equal to mu s into gr. Now this part, under root mu s into g, this part is a constant. R can vary. So from here we can write that the maximum velocity that I can achieve for the vehicle on this road, on the pair of the conditions of the tire and the road, which define the frictional forces, we find that V max is proportional to R, power half, or under root R. And so if I plot under root R the root over of the radius of curvature, which is in meter to the power half, velocity maximum meter per second, then we get a slope, and this slope for a given mu s is equal to mu s into g under root over, okay, which I get here. So very interesting thing is that the more the value of R, the more the V max that we can have. And I told you that what is, I want you to recall what is the relation between curvature and radius of curvature. Then I told you that the curvature and the radius of curvature, they bear a very simple relationship, that if I plot the curvature and the radius of curvature, then I'll get a asymptotic curve like this, because the curvature into the radius of curvature is defined as equal to 1. So the less the radius of curvature, the more curvy the thing is. And for example, a point is the curviest of all circular circles where the radius of curvature is tending towards equal to 0. So in this situation, we can find out, suppose R is equal to, I mean it's very large, it's approximately infinite, okay. That means we are not going on a circular path, we are not leading a circular path. Then we can have anywhere, theoretically speaking, we can have any value of V max. Of course, other kind of physics will come which will limit that physics is the dissipation of the tires and the heat which is produced over there, the heat which is accumulated over there, etc. Okay, so after taking the case of a car or a vehicle going on a plane surface, making an angle R, now I take up the case of a road which has been purposely banked, okay, to deal in the exercise of taking up a curvature of the road. And here I make a schematic diagram. Well, this is my car, and on the car I have one of the forces here is mg in the downward direction, okay, and this is the normal force normal to the road, and this has been resolved into two parts, because this angle over here is also theta. If we see, look at geometry, you make it yourself, then you find that this angle is theta. So this n is resolved along this direction as n cos of theta, and the frictional force is in this direction, is parallel to the road, and the mv square upon r is toward the center of the circle that the vehicle is going to take. So this is the description of what is happening on a banked road. This bank is not a State Bank or any other bank, ICICI Bank, etc. But this is the bank of a river. The term comes from all rivers have a bank, which is normally can be described in terms of an inclined plane. So on this inclined plane I have my car, and the car is moving. It may move with a certain velocity. We have to see as to how much velocity it can achieve, and then we make the free body diagram. The free body diagram which I do here, I have the various forces. One is the force of friction, which is along the slope, and the other is the normal force, which is 90 degrees inclined to this plane, because it has a normal, it has to be a normal force. Normal means up with the 90 degree. Okay, so look here, when we resolve these forces, then n is resolved in one part as n cos of theta. Okay, and I have this angle also equal to theta, and this angle is also equal to theta. So we find the angle between this and this is 90 degrees, and also between this and this is 90 degrees. So it shows that there is n sine of theta. Actually, in cos of 90 minus theta or pi by 2 minus theta in this direction, and this is also fs cos of theta in this direction. Okay, now this is what provides this set of forces together. They provide the centripetal force, which is mv square upon r, as per what I told you before. Then looking into this, I can say that n cos of theta, this force here, this is balanced by two forces, f sine of theta, the resolved part in this direction, because this angle is again equal to 90 minus theta. So this becomes f cos of 90 minus theta, which is f sine of theta, plus the mg force, and then we can write the equation that n cos of theta is equal to mg plus f sine theta. This is one equation that we obtained, and the second equation is the provision of the mv square upon r force here. So I say that n cos of theta, n sine of theta plus f cos of theta, this provides mv square upon r, which is essential for the centripetal acceleration, which is, and this is mv square upon r is centripetal force. But because we have been taking the static friction, the limiting friction, the friction should be smaller than equal to mu s, the coefficient of limiting friction, multiplied by n, the normal force that exists over there. So to obtain the velocity maximum that we need to calculate, what we put is, we remove this sign and simply put that my force of friction is equal to mu s into n. Then equation number 1, I write here mu s into n, and then I can write the value of n as equal to mg, because this another n into mu s sine of theta comes on this side, and then finally we get the equation 1 dash, which is n is equal to mg upon cos theta minus mu sine theta. I'm not going to spend much time on that. And from equation number 2, what we can obtain is for the maximum velocity that I have just introduced to you, n sine of theta plus f cos of theta, which is equal to mu s into n cos theta, is equal to m v maximum square upon r. So what we obtain with the help of these two equations, I can therefore write that the value n, which is mg upon cos of theta minus mu sin theta, mg upon cos of theta minus mu sin theta here, this multiplied by sine of theta, because I can take in this relation a 2 dash. From 2 dash I can take n as common, then I get sine theta and mu s cos of theta within bracket. So I obtain this relation, which is providing the mv max square upon r, and so that v max square I can write as, because m and m will cancel out here, and what I have is this relation. Okay, I obtain a relation over here like this. V max square is equal to gr into, now I divide the numerator and denominator both with cos of theta, so it's a simple exercise, trigonometric exercise, and then this becomes equal to mu s into cos theta upon cos theta is equal to mu s, and this sin theta upon cos theta is tan theta, and similarly I obtain here 1 minus mu s sin theta upon cos theta is equal to this. Okay, so this is a relation that we obtain for the maximum velocity which occurs under the limiting friction. So my V max becomes equal to under root Rg into mu s plus tan theta divided by 1 minus mu s tan theta. Remember, all these mu s tan theta, they are all mere numbers. So I obtain this relation for the maximum velocity that can be obtained like this. Now under a condition that if mu s is equal to 0, that is, there is no friction, then in that case we see that V max at 0, this becomes equal to, because this becomes equal to 0 and this also becomes equal to 0, so I am left with tan theta, so this is equal to under root of Rg tan theta, which gives the maximum velocity, which you can compare with the previous example that we had taken, and you will find that the banking is the better alternative, and by doing the banking we provide to the vehicle a longer life, less wear and tear, which is not desirable, and at the same time what basically happens is that there is a power dissipation, and we want to minimize the power dissipation so that the tire life of the tire is improved, etc. So I have in a way talked about friction, which is desirable as well as undesirable. I have taken the cases of vehicles moving on the road. We have taken the limiting friction, this is static friction. In both this example and the previous example, in both the cases we take those things and we obtain certain relations which make us give us interesting results. Okay. For example, here also you can see, because g is a constant, for a given theta, tan theta is also a constant. So again this V maximum is proportional to under root of R. So if R is more, then curvature is less, okay, less, and V maximum is given by under root of g tan theta, which is constant. And in this case, if I draw the same kind of a graph, that is, what will be the value of V max 0? V max 0 here in meter per second, and under root R, which is per meter, then we find that there is a slope, and the slope is equal to, slope interestingly is equal to under root of g tan theta, and we come to an end of this exercise. If there is an occasion, we can revisit that, and that occasion will arrive only when you ask me a question in the comment section, because I have been receiving some answers some questions in the comment section, which some of the recipients, boys and girls, teachers, they are asking certain questions. I need your questions to improve upon the contents of my endeavor in the doing physics. I have enjoyed. Hope you have also enjoyed. So long. See you again.